So now I'd like to bring Ken Finnegan. AA Ireland, I think, is what Conor called him earlier on, but he's the Chief Executive Officer at Tangent, Trinity's idea workspace, to the stage, who will facilitate the QA with our next speaker, Dr. Heidi Christensen from the University of Sheffield. So Ken, welcome to the RDI. I hope. I know this is unusually, this is only your second visit here. Like I think when you came for the launch in February last year, I think we thought you'd be coming down every quarter, and then this COVID inconvenience happened and we haven't seen you since, but it's great to have you back. Lovely to have you here. Thanks as well for Tangent becoming a key partner in this year's John McCarthy AI Summer School. And I suppose to start with, can you talk to people a little bit about Tangent? And I know you're going to have two of our speakers tomorrow have been very involved in Tangent in recent times, with your AI accelerator and your launch box. So I'll hand over to you, Ken.
Thanks very much, Liam. It's a pleasure to be here. So Tangent is Trinity's Ideas Workspace. In Tangent, we aim to bridge the gap between the university and the wider startup ecosystem. So we collaborate with companies large and small who play an active role working with our startups, our students, and on their own professional development programs that Tangent offer. So Tangent is Trinity's Ideas Workspace. We provide access to a variety of mentorship programs inspiring the next generation of learners, entrepreneurs, and startups who will all provide meaningful impact in the world. It's also home to Launchbox Trinity Student Accelerator, which only finished up last Friday actually, and our most recent accelerator, which is the AI accelerator at Assessor, and we run in partnership with Altata, one of the most successful SMEs in Ireland at the moment in artificial intelligence. 2021 was the inaugural year for the AI accelerator. After 5 months of honing their startup, 6 finalists competed to secure $250,000 in funding, courtesy of Oyster Haven Ventures and Rocktop Partners. This year's AI accelerator winner, Impeel, and actually Field of Vision, the runners-up, will present here at the school tomorrow, so we're excited to see them tomorrow. And just for any startup interested in participating on our accelerator, Assessor, we will begin to accept applications for the accelerator starting about mid-October. So if you're an AI startup with a great idea, don't hesitate to get in touch.
Yeah, Ken, I'm probably going to take you back a little bit to before your Tangent days, back to maybe what Conor was talking about earlier on, because I know when you were in the IDA, you were driving a lot of stuff, strategy around AI, and as Conor was saying, making an AI Ireland or whatever like that. Yeah. How have you seen developments in recent times? Like I know there was a recent strategy document that came out around AI for Good. How do you see the developments that are happening in recent times around AI on the island?
You know what, it's been an amazing journey actually. So previous to my role in Trinity, I was in chief technologist in IDA Ireland, and I was given the order, if you want, or the opportunity to develop kind of like the national proposition around artificial intelligence for Ireland. That began around 2015, 2016, I think. And I remember when Leo Clancy, who's the head of Enterprise Ireland, he was my boss in IDA at the time, had come to me with the idea of kind of like looking into artificial intelligence. What sprung to my mind was the robots are coming, kind of like the Terminator 2 type things. But we pulled together kind of like a group of 100 people that represented SMEs, multinationals, academics. We had the unions present, we had government agencies present, and the whole idea was to kind of like look at what is Ireland's proposition around artificial intelligence. So that was the seed of kind of like understanding what the future might look like for Ireland. So that was where AI Ireland and the concept of AI Ireland came from as well. And subsequent to that, then it's been a journey to get to, I guess, the most recent highlight from a national perspective is the national strategy that was launched by Minister Troy at the beginning of summer in Tangent. So we're really proud to have been involved in that, but it's also from inception, if you want, to where we are now. I think Ireland as a country, we're in a really, really strong position. Like foreign direct investment, technology companies, and technical capability have been here for quite a long time now. So we're not starting from a kind of like a blank sheet. We're starting in a very kind of like enviable position, if you want, compared to a lot of other countries.
No, I couldn't agree more. And look, Ken, I think reading the recent strategy document, it's a testament to where things have come and the vision that you had, when you were in the idea to bring it forward with Leo Clancy. So well done. So I'm going to hand over to you now, Ken, to intro our next speaker, which again has a tough act to follow after Conor again, but I'm sure you'll do well.
Very good, thank you. So everybody, you're in for a treat with our next speaker. Dr. Heidi Christensen is a senior lecturer in computer science at the University of Sheffield, a member of the Centre for Assistive Technology and Connected Healthcare, CATCH, at the University of Sheffield. Dr. Heidi Christensen is part of the Speech and Hearing Research Group, SPNH, and a theme lead with the UKRI Centre for Doctoral Training in Speech and Language Technologies and their applications. She is also the technical lead for CognoSpeak, a speech-based tool for detecting and tracking early signs of cognitive impairment. She joins us today from Sheffield to talk about how speech signal technology can be used to advance healthcare. Heidi, welcome, and over to you.
Thank you very much. So I've just been guided through how to share my presentation in the meeting, so let's hope this works. I probably need a little bit of feedback whether everyone can see this now and hear me, of course. Okay, I'll assume I'll be told if you can't. So thank you so much for inviting me here and giving me an opportunity to talk to you and talk to you about what is really close to my heart, how we can use speech technology to kind of advance healthcare. So as you heard there, I'm working at the University of Sheffield. I'm originally from Denmark, but I've been there for 20-something years. This is a PDF of my very carefully crafted keynote presentation, but apparently that doesn't really work with Microsoft. But let's hope it's not too kind of distorted. So I wanted to first talk you through sort of general healthcare applications of speech technology. So you probably know the very distinguished professor on the right here, Professor Hawkins, who was a very keen and adamant kind of user of speech technology in general. So the types of speech technology we talk about is mainly speech recognition. So that's taking speech and turning it into text. Speech synthesis, so that's kind of going the opposite way, which Professor Hawkins, of course, made use of for a long time of his life. He got very devoted to his voice, and although technology moved on from this very distinct sort of robotic voice, he was insistent that he keep that because it kind of was part of his personality by then. And then there's speech analysis, so in general sort of measuring aspects of speech, for example, how well you pronounce something, or signs of dementia, which is something I work on. And then there's speech processing in general, so altering the speech signal in many different ways. But for example, in kind of working with speech pathologies, you might be interested in trying to make speech more intelligible. So all of these different types of applications, if you like, involve different aspects of IA. In all the different ways that we kind of can define AI, so both in the way of trying to give machines more human-like capabilities, making it understand speech, making it talk, but also, of course, in terms of machine learning, learning general patterns through data. My key interest is in pathological speech, and in particular in how we can use technology to improve the lives of people with pathological speech. So what do we mean by this? Generally, when people have communication order, your normal or typical speech is disrupted. So this can be caused by a number of different conditions, for example, cerebral palsy, stroke, or cognitive impairment. I'll talk you through some of these in a bit. So how can automation and AI in general kind of contribute in this sort of space? Often when we've got AI powered tools, it makes things faster, cheaper, more repeatable and more objective. So these are some of the reasons why we might go down the line of trying to apply AI. Computers can complement the analysis that humans might do in routine care, clinicians and health practitioners in general. And we can kind of see automation as a way of augmenting healthcare provision, which can mean, for example, increased access to data points outside of face-to-face meetings. So often when we start talking to clinicians about what the options are, there is a misconception that we're trying to replace them. And very rarely is that the case. Instead, we're trying to perhaps free up some of that time to be spent on the more kind of useful, high quality, if you like, interactions they have with patients, and then provide them with sort of additional information along the way. So I just wanted to think a little bit about the impacts on quality of life that speech technology in general can kind of bring. So I've just outlined in the rows here the different sort of broad types of conditions that I've worked with. Of course, there are many, many more. So something like cerebral palsy is a good example of a kind of lifelong condition. You have it from birth, normally from complications during birth. So it's for life. And somehow it becomes normal for that person and the family. But in terms of impact on quality of life, the impact is huge and sustained in general. Something like stroke or traumatic brain injury from, for example, an accident. The duration can be anything from a few weeks to for life, and it's normally a very abrupt occasion, of course, with not many signs leading up to it. So you might go from one day leading a very active and working life, and then suddenly be severely impaired. And there's a long process of kind of rehabilitation afterwards. So the impact on your quality of life, of course, is huge. A lot of change and a lot of things to deal with very suddenly, but also with some hope of improvement with time. And contrast that eventually or finally with dementia or ALS, for example, or other neurodegenerative conditions like Parkinson's. So here we are thinking about it's a very slow onset late on in life typically, and the rate of degeneration kind of varies. But mostly these are fatal and chronic kind of conditions, and there's a lot of anxiety and uncertainty connected with this, and this sort of sense once you have the diagnosis that things will get worse. So for that group of people, it's really important that we help them and their families to perhaps get diagnosis early without too much anxiety and waiting, and then being able to give them the right support throughout. So thinking a little bit about how speech technology might make a difference, and this is a totally non-complete list of things that we can do or hoping to be able to do. The sort of obvious starting point, I think, is dictation. So even just 10 years ago, even for people with typical speech, it was not possible to really have good dictation systems, or they were a bit clunky. But these days, of course, we're all able to dictate emails, etc., and messages on our phones. It's widely available. So it's sort of, in some senses, sorted or solved for typical speech. But of course, for pathological speech, we are way behind. And that for a lot of these people, for example, people with cerebral palsy, would make a huge change if they were able to dictate, for example, an email or documents in general. Communication aids is also really important, especially if you have severe cerebral palsy with a sort of severe speech impairment. And in general, spoken language interfaces that we're now becoming so used to on your phones, in your homes, various smart speakers, people speak to their cars. That's all becoming totally pervasive for most of us. In terms of therapy and rehabilitation, there's also a lot of need for speech technology to kind of automate and give really objective kind of evaluations. And then in general, there's a kind of intelligibility assessment that is also really useful. So people are working on all of these areas, and I have to say, probably along the lines of where typical speech technology now is moving into the big companies, Google, Amazon, Microsoft, etc. More and more people in the sort of academic world are interested in these more niche areas, for example, with pathological speech. So that's a really exciting time for us. So I want to talk about just two things really in this talk, which are the two main areas of research I'm involved with. So how we can improve communication ability for people with atypical speech, and the kind of core building block there is speech recognition. And then how we can detect signs of pathology in a person's speech and language in general. So in terms of improving communication ability, the core motivation here is that people with atypical or dysarthric speech caused by long-term conditions like cerebral palsy or brain injury or stroke find it hard to communicate effectively with other humans and with machines. So there's kind of a double whammy. So their close family will understand them and care us, but in generally they can be quite difficult for other people to understand, and certainly this carries over into machines that are kind of trained to recognize human, typical speech. So they can't use current speech technology, and in addition to that, they very often have mobility problems. So they struggle to use other ways of communicating, for example, with machines, so keyboards and mouse and trackpad and all of those other things. So if we were able to give them a speech-enabled interface, the impact really would be for life. And some examples down here for kind of applications that use speech recognition. And I've worked on all of those. Now this here is the video, which unfortunately I'm not able to play to you. But this is a guy called John Toogood. So he's a kind of gold star user in our Catch Centre. And we've worked with him for probably 15 years, if not longer. He's donated a lot of speech, but he's also been absolutely crucial as a co-designer on the projects. We've worked with him a lot. He's got moderate to severe dysarthria. And what I normally do is play him talking a little bit about this communication aid that you see here. And the first time I play the video, I play it with a sort of a line across the captioning. So it's a bit like watching a film in a foreign language and you're just really struggling to quite cue into what's being said. And then I play it again without with the captioning, and you then realize that it's not like he's not saying all of the words. He is saying everything grammatically and like anyone would say. So it's not a language production problem, but it's purely a speech production problem. And you kind of, as you can read the words at the same time, you can kind of cue in. So there's little extra cues that help your brain to kind of perceive what it is John is saying. It's a bit like if I'm watching a French film, for example, if the captioning is on, I'm just a little bit better at my French. So what are the challenges of recognizing dysarthric speech? Why is it that this is actually very difficult, given we've sort of come such a long way with speech technology for typical speech? So I assume quite a lot of you are not familiar with speech recognition. So this is a one-page crash course in automatic speech recognition. And the reason I'm showing the slightly complicated diagram is just for you to be able to kind of see what parts of an automatic speech recognizer might struggle when it is exposed to speech which is not sounding like typical speech. So on the left here, you've got a person speaking, and we then have an acoustic front end that is processing various typical kind of speech processing or signal processing algorithm here to reduce a bit of noise, etc. And then we extract features, and feature here means key bits of information, and that's sort of honed down. So even for people with dysarthria, you would probably extract more or less the same information as you do for people with typical speech. And those features are then passed onto the decoder, the kind of search algorithm. And that search algorithm in sort of classical automatic speech recognition systems make mainly use of three models, as you can see the red arrows here. So the acoustic model, telling you a little bit about the phonemes and the kind of sounding blocks of speech. A language model that tells you, it's a sort of probabilistic model telling you the sort of likelihoods of particular words appearing after other words. And then a pronunciation model at the sort of word level telling you what sounds are more likely to appear after each other for particular words. And all of these are kind of specific to the language. But normally for typical speech, you could record perhaps 1,000 hours or 100,000 hours like Google might do, and put all of that speech together and train really, really powerful models. But for dysarthric speech, sometimes that's not possible because they each sound very, very different. And so you're ending up having very, very small amounts of data to train this with. And I should say that this is a sort of traditional speech recognizer. The modern ones, as you might have guessed, is kind of going down the route of deep learning. And what really happens is that you might start with the speech in on the left side, and then everything else is a big deep learning model. Those are currently the sort of strongest models, really, but they take a lot of data. And of course, when we're working on pathological speech, we just don't have anywhere near that amount of data. So we're stuck with this kind of model and will be for some time. But it also gives you opportunities to tune each of these. You can imagine if you have a particular speaker who are struggling with particular vowels, for example, you might be able to tune the acoustic model to take this into account. So that was a crash course in automatic speech recognition, or ASR, as we say. So I just wanted to talk you through a little bit about what we then see in this dysarthric speech compared to typical speech. And on the right here, don't worry too much if you can't read the labels and everything, but basically you've got dysarthric speech at the top and non-dysarthric speech at the bottom. And the thing to look at is each ring is a kind of distribution, if you like, in frequencies of different vowels, and the rings at the top are much broader than at the bottom. At the bottom, they are sort of spread out a little bit. They don't overlap too much, but at the top, there is a lot of overlap. And that is basically indicating a sort of lack of consistency in the way people are able to use their articulators. So everything sounds a little bit the same, and they're not able to make the different phonemes or the different building blocks of sound distinct enough. And that makes it really hard for human ears to hear, and it makes it really hard for computer ears to really make sense of. However, the last bullet point here is a really important point. So people with moderate to severe dysarthric speech are understood by close friends and family. So for example, John, that you didn't see on the video, but just saw a picture of, his carers, when I go to visit him, and his family will understand him more or less 100%. And so what's interesting about that is that it gives us hope from the kind of machine learning perspective that these variations are not random at all. They're produced by this physical system of articulators moving a little bit differently than people without impairments. But there is information in there that can be learned by the human brain, so we should think that we could also learn this by computers, which is good news. So to summarize, the kind of main research challenges are to do with data. So when I say they've got 100,000 hours or something in Google, that's not an underestimation. So they really have, every time you use your phone, they will collect that data and add into their model. But in my world, we've got maybe 20 minutes from one person or a little bit more. So a lot of the work really is about how we can build a well-performing speech recognizer from these very, very sparse data sets. So for each individual, it's really tiring to record many hours of speech. And so that makes it impossible. I can't say to, for example, John, you know, over the next 3 weeks, can you record 100 hours for me? That's just not possible. It's a sort of whole body thing for him to record or speak. It's also difficult to get transcriptions, which means having a text file of basically saying which words were said in this bit of audio. And that's really important in terms of AI machine learning, because we train with a sort of parallel corpus of the audio and then lists of which words were said. Normally, if I went to record 100 hours from someone, I could give it to some students in my lab and say, you know, listen to this, I'll pay you some money, and write down what's been said. That's not possible with someone like John, because everyone's struggling to really understand what he's saying, except if you ask, for example, his family to help us transcribe. And of course, in the long run, that's not feasible. So it makes it just harder to get going on the research. And also, there's hardly any found data. So for the sort of main stream speech recognition work, there's a lot of work on kind of information from database and TV, etc. We haven't got that. And also we need to personalize. So the speaker independent models do not generally work well. So we really need something that is specific to that person. I'm just going to speed up a little bit because I can see we did a little bit of faffing about in the beginning. So this graph here shows you the involvement or the development from 1970 for mainstream ASR, the very basic systems, command and control, detection systems, personal assistance, and kind of interactional systems now with robots and virtual agents. And this is where dysarthric ASI is. So way, way back, you know, back when I was just born. So we really have a lot of work to do. So how far have we come? What else general work kind of focused on? I'm going to go through this. So if you're not very familiar with speech tech, hopefully you'll understand some of the higher kind of levels. So one of the things people have done is trying to do model adaptation, taking these typical speech models and try and morph them in or adapt them onto something which is a bit more suitable for dysarthric models, all of the models we saw on that slide. There's also been a lot of work of trying to increase the amount of data using general sort of schemes for this, trying to use out-of-domain data, trying to pool it with typical data, try to do data augmentation to try and permeate the data we have. And then there's been work sort of doing the opposite, almost taking the dysarthric speech and trying to make it sound a bit more or appear a bit more like typical speech, in the hope that we then might be able to use these really powerful typical speech ASR engines. And there's also been a lot of work to try and find better encodings. Perhaps we could use articulatory data in supplement to the acoustic data to try and get a better sort of higher dimensional angle to the kind of speech signal. That was an idea we kind of visited probably 20 years ago in mainstream ASR. It didn't really work because we ended up having so much data. But there is a hope that this might be a way of working with dysastric speech. And people are also investigating using video, so having a multimodal ASR system, because there's a lot of information by watching a person's kind of the way they move their mouth and head. And in general, kind of using some tricks here, so you may or may not be familiar with some of these approaches here by I-vector and speak invariant kind of features. And of course, recently we have tried as best we can to move into deep learning, starting with some of the less data hungry kind of approaches, and sort of all the while sort of revisiting all of the above, if you like. So we have a long line of Sheffield work here. I didn't want to kind of give you too many slides with all of the work, but just kind of want to mention a few key things. So home service is an early work. Probably 10 years ago, I worked on this, where we put systems in people's homes and tried to record data. And these were just recognizing one single word, but it worked remarkably well once you have a lot of data from one person. We've done some work on using articulators. Again, things work well, but we need more data. Transforming of the speech, that also works to some extent. We have to be quite difficult not to break things, if you like, in the modeling. And then recently we've worked a little bit on emotion recognition to try and see if people with dysastric speech can express emotions, and they can. So that's good news. There's a lot of commercial interest now. So Google are collecting speech. Just this week we have a big speech tech conference, and they have a paper tomorrow actually on 100 million utterances, or words, I think it is actually, but they're not releasing the data, so this is kind of staying within Google. And other companies, VoiceIt and Therapy Box, are working on this. So let me move on to the other half of the talk, which is on detecting signs of pathology in a person's speech and language. So this is something I've started working on in the last 5 years, I would say. As we get old, of course, dementia is an increasing kind of risk, and it's a sort of cognitive impairment which is the result of various conditions, for example, Alzheimer's disease or Parkinson's. And people often show very early signs of the condition in their speech and language, which are too subtle sometimes to be picked up by people in their kind of families and carers, etc., but may be able to be picked up by automatic speech recognition algorithms. So famous examples where people have looked at how people's language change over time. For example, Iris Murdoch, the famous British author, people compare the speech or the language in her books and found towards the end that it was much empowered. And the same with Ronald Reagan, where his speeches or kind of press conferences people looked at. And of course, he was diagnosed with Alzheimer's disease, I think 5 years after he left office. So the current diagnostic processes are basically pen and paper. So there's this mocker test, for example, where people kind of look at different things. It's a very simple test in some ways. This is the test that Donald Trump famously trumped, or aced, I think he called it. So all of it's very straightforward, unless you've got cognitive impairment, then you start kind of worrying or showing signs. In general, we're interested in detecting dementia because there currently are a lot of people going to see the doctor with memory concerns, and the GPs are not very good at actually accurately finding out whether they should be referred to secondary care for further investigation or not. So at the moment, lots of people get referred just to be on the safe side, and these are very, very expensive assessments. So what we're really hoping is to give the GPs this tool that can better help them make that decision, because lots of people have problems with their memory, but not all of it is to do with dementia. So it's better if they could be seen early. So we looked at analysing people's conversational abilities. First, just recording patients speaking to doctors and see what came out there, but eventually making a digital doctor like the one I've got on my right here, on the table that are asking people some memory probing questions, and we're then using AI to kind of try and look for particular patterns in the way people answer these questions, hesitations, choice of words, empty phrases, lots and lots and lots of things we're extracting and then using various classification algorithms to try and unpick what's going on. So this is an animation as well, but obviously not on a PDF. So what we're kind of doing is analysing conversations between the patients and his computerized head, and basically just making this decision between low, intermediate or high risk of dementia. So that's what the GP can kind of use to decide whether they should refer to secondary care or they should provide different types of care for the patient. And of course, when you have systems like this, you have to be really, really careful with the errors that you're making. So we want to prevent lots of people going to the secondary care for expensive analysis if they don't need to. But what's even more important is, of course, to avoid anyone being misclassified as being low risk of dementia when really they are at risk. So we're trying with the machine learning to really move this sort of decision boundary to avoid those kind of false negative classes. And I wanted to just go through a few other things that is happening in Sheffield related to this. So we've done a lot of work on automatic ways of analysing picture description. So the picture here on the right is an example of a very classic picture that you give to people. It is totally politically incorrect these days. I do a lot of work in kind of equality work, and I'm not happy with it. But anyway, it is what it is. But it's a very 50s sort of paper, isn't it? Picture. And the idea is that when people start describing this, if they have cognitive impairment, they may fail, for example, to recognise that the children are probably the children of the woman, and the woman is their mum. And sometimes they might not notice, for example, that there's a bit of a disaster with the tap and the sink. So those kind of things, so they will kind of jump around and perhaps talk about the lady rather than the mum. So those kind of subtle things, when you've got 100 or more description, you can kind of start seeing how the language changes and also how they kind of jump around in terms of the topics they cover. Other things we've worked on is stroke survivors, again, to try and give automatic ways of monitoring cognitive impairment. For, of course, once you've had a stroke, there's a lot of rehabilitation and further assessment. You spend a lot of time in and out of hospital. So if you could be at home and do some of the assessment on these kind of automatic tools, this would be really nice. And similarly, we work with patients with mild cognitive impairment, which can be a stage to dementia, and we sort of monitor whether they convert, as it's called, to Alzheimer's disease, and a couple of other things that we're kind of working with. I'll skip over this in the interest of time. So currently we're working with a company called TherapyBox to commercialize CognoSpeak, which is taking all of the kind of speech analytics and the machine learning and with a nice front end to put this tool in the hands of GPs to really start collecting even more data. And I wanted to finish with an additional kind of item, having covered the kind of my kind of research topics here, but just thinking a little bit about the main challenges for working with healthcare applications and sort of AI. So there's many things to consider, and as you will probably have taken from the speech so far, talk so far, one of the key things as a researcher is this kind of difficulty around having access to sufficient and sufficiently good speech material. So the data sets are small, and often they're collected with particular ethics. Certainly in the UK here, it's very difficult to be allowed to collect data from patients and then also be allowed to share it, as it should be, of course. But what that means is that you end up with these researchers across the globe that each have a small data set, but there's no way of pooling all of this together. And of course, for AI and kind of machine learning, that's kind of key for us to upgrade our models, if you like, into something that's a bit more state of the art. The data that we have got access to have not necessarily been recorded for speech recognition, if that's what I'm interested in. So, for example, in the world of disordered speech, there are a couple of data sets that they're tiny, but also they were recorded for slightly different things, and it means it's just there's some peculiarities with the data that just makes it a little bit different in terms of the AI and the kind of machine learning, to be careful not to sort of build in a little bit of bias in there. Also, if you're kind of recording data, it can be very messy. So I'm very, very fortunate to work with a neurologist in the local hospital just down the road, really, from campus in Sheffield. And he's been really helpful in kind of recruiting patients and getting them through this. But ever so often he will kind of update various cells in our kind of shared spreadsheet with diagnostic categories, because for him diagnosing dementia is quite a grey area, and so things labels change, and that's a little bit annoying. If you're doing machine learning, of course, you then need to retrain your models, but that's just how it is. And of course, we want to have the best quality category, so we really welcome that the labels get improved, if you like. And then a lot of the data sets are basically lacking a lot of standardized setups, which probably, if you have a speech tech hat on, is of more interest here. And there's a little bit less good practice around sort of making scripts available and having everything open source. And then I'll say also, when working in sort of healthcare applications coming from an engineering and kind of computer science background, it's really important that you bear in mind that you are developing this for people. It has to be useful and it has to be usable to your user groups. And you've got different types of end users: carers, clinicians, patients themselves, or people with memory concerns themselves. So do a lot of co-design workshops if you can. Try and take on board early ideas and projects and take them to PPI groups, so get patient and public kind of involvement early on. We've learned a lot. You really cannot assume anything, and through that sort of do repeated kind of evaluations. And then, so my final slide here in terms of top tips: work closely with clinicians if at all possible. If you are coming from an engineering computer science background, it's great fun, and try and embrace the sort of multidisciplinary aspects of projects. That is super challenging, but also for me certainly really, really rewarding. Everyone coming from the different cultures in terms of research background, and really trying to find a common language. And in that sort of area, be careful with your own language. When I'm reviewing other people's paper, I try and really put this down. But for example, we're using a word like normal. We should be using the word typical for typical speech, for example. Be careful using the word patient if people are not in a hospital kind of setting, talking about people suffering from, etc. But these are all things for us to kind of learn along the way. And most of all, sort of enjoy and throw yourself out in it. So this is just hopefully a complete list of my collaborators, students, etc. Thank you so much. I'm going to try and navigate back to teamwork here.
Thank you, Dr. Christensen, for a great presentation. I think like part of the whole program for the summer school is to demonstrate wellness and multiple different applications with regards to AI, and the work you're doing here is incredible in terms of a very specific cohort of individuals. So well done, and thank you for a great presentation. We're now going to take some questions from the audience. So if anybody has questions, please pop them into the chat. I have some lined up already. So without further ado, Liam asks, Dr. Christensen, what are the ethical issues you have to overcome when gathering speech data?
That's a very good question. Do just call me Heidi. Yeah, so it's very, very interesting because, of course, with speech data, you are totally identifiable. If someone's heard you talk before, they can identify you, and that is a big issue. But it's somehow seen as less intrusive than if we were to record videos. So people, for example, would be happier to have audio recordings in their home rather than video recordings. Secondly, of course, you have to be really careful when with what you are asking them about. So one of the things we are interested in is to what degree can people remember, for example, what did you do over the weekend, or what did you do when you left school? And of course, there will be personal information in there. So we try and take some of this out, but at the same time, if you are wanting to have high quality labels of what people said, you can't anonymize everything because it doesn't fit with the audio. So there is a lot of work there. So we do not tend to share any of the data we record, for example, with our cognitive speech system for those particular reasons. Yeah.
Very good. We have a question in from Claire. How do you remove the noise or bad data gathered with the speech data gathered?
Yeah, I would say actually removing background noise is less of a problem these days. Even with a sort of simple laptop, you can get an okay speech to noise ratio, as we call it. I'm on a different project working with people who found some cassette tapes of mums talking about their twins, probably about 50 years ago. That's noisy, and that is difficult to kind of work with. But modern technology, I'd say you have a pretty good way of doing. There's still work you can do. In terms of speech in general, speech recognition, the biggest noise is often from other speakers. So, for example, if you're in general working with conversational data, people with overlapping speech, that's difficult to handle. And so we see that a lot with, for example, our conversations. You might bring in your spouse and they will kind of, as couples do, they've known each other for 40 years, talk on top of each other all the time. So that's tricky in terms of the AI. And
like, are there any applications that you'd recommend, or are there any kind of like methods that you recommend above others for recording?
Yeah, so of course we would have a lot of kind of in-house methodologies and approaches, but there are in various kind of recording tools like Audacity, they might know that there are kind of noise reduction algorithms in there you can use. You sort of get the tool to look at a section without speech and just look at what the background noise is, and it will try and subtract it in a sort of signal processing way.
Okay, excellent. Rating has asked, are you focusing on adults for research, or children included in the research and the data?
I haven't worked with children, but I would love to. So, for example, on the kind of communication aids in terms of people with cerebral palsy, of course, it's for life, and really, I think they should be given a communication aid, you know, very, very early on, so they can start communicating straight away. Going back to previous questions, that's where often ethics is kind of a little bit problematic, because you getting access to children, being allowed to record enough data from them can be difficult. But yeah.
There's a wonderful company called Soapbox Labs here, based in Ireland, that are getting global recognition around children's speech and children's learning. Maybe we can connect you in with those guys as well. For
yes, I have. Yeah, I think I have a colleague who's gone there. Yes, absolutely.
Shared learning. Okay, very good. Jen asks, do you have a sense of the financial benefits for the NHS or the HSE of your tools by reducing the referrals for people presenting with memory issues?
Yeah, we did just get a big grant where we all applied for a big grant, so we have to kind of estimate that. So I think potentially there are millions to be saved by the NHS because it's such a bottleneck. Obviously, it's a long process. You have to kind of demonstrate the accuracy of what you're doing. But these kind of expensive assessments, the scans and blood tests, and etc., they kind of add up. And of course, clinicians' time, so neurologists are not cheap. So the more we can channel their kind of time into looking at the right patients, the better for everyone.
And just as a curiosity, can you tell me, like, in terms of percentage of the population that would be impacted by speech challenges or issues, like what would that look like?
Yeah, so I didn't actually mention that. So something like dementia, I think it's 850,000 in the UK. So it is actually the biggest killer in England and Wales. So I don't know for Ireland or the rest of the world, but it is an increasing problem because we live longer. So it's bigger than heart disease or cancer or those kind of major things. It receives a lot less funding. And one of the issues at the moment is that there's a lot of research going into trying to find treatment, as you can imagine, but it's, you know, there's very little you can actually do. But once you have that, of course, there's a lot of interest in trying to detect people early.
And isn't that it? It's kind of like, it's like we're living longer, but not the quality. Our quality of life isn't necessarily matching the longevity of our life.
Yeah.
I have a question in from Liam. How do you gather emotional recognition data from humans?
That's a very, very good question, and a big debate in the speech community. So well perceived. There's basically two approaches. One is to ask people to read sentences and imagine they experience a certain emotion. The advantage of that is you sort of know what emotion at least they're aiming to do. Sometimes you have voice actors doing that. They're a little bit better at it than us normal people. but sometimes that's not always possible. The other approach is to just look for, I don't know, something like EastEnders or various kind of shows or television programs, and try and guess what, that definitely they sound disappointed or they definitely sound angry. But of course, then the labels become a little bit uncertain. So there's these two schools of collecting data, and they none of them are perfect, I would say. But in our case, we went for the prompted and try and act, because of course there are very few people with dysarthria in soap operas.
That's really interesting. I'll try and add more inquisition to when I'm asking questions here. And so Craig asks, what software is used to store this data?
To store it?
Yeah.
Yeah. Well, we sometimes use sort of general typical databases to kind of manage it, but otherwise we just kind of store it on our servers in Sheffield. Is that what I meant, to store it or to process it? The storing is kind of pretty straightforward. The processing, in terms of we use a lot of high performance computing and GPUs and that sort of thing.
I guess it's like, is there a preference in terms of do you use any of the kind of like the Microsofts or AWSs or Googles, etc.?
Yeah, so for this type of data, we're not actually allowed to store it outside of the secure servers in Sheffield. So we can't use, for example, Amazon's cloud-based servers or anything like that. So it is stored in Sheffield for this data.
Okay, so maybe that's the question that was being asked. So
yeah. In general, the kind of processing systems, that's why I was a little bit unfamiliar with Microsoft, is Linux and Unix and that sort of way of working on computers. Yeah.
Very good. So Jessica asks, is this research being done on speakers of languages other than English?
Oh, very good question. We are just in the process of doing exactly that, or I should say, rather looking at people with non-English native backgrounds, so like myself, for example. So of course, in most Western countries these days, it's a very multi-ethnic population. Of course, as they grow older, they also need to have access to, for example, these tools for detecting dementia. But how do you do that for someone who's not fluent, perhaps, in English? So we're trying to look at how you can kind of mitigate that with the kind of tools, try and see how you can better accommodate people that comes from a slightly different language background.
And have you found, or do you partner with other universities in different parts of the world, or is this just a research program happening in your institution?
Yeah, a bit of both actually. So there's thankfully a lot of work happening all over the world, from China to Brazil to Colombia to so lots of different languages are kind of represented in this world, but it's always dependent on people getting funding to record the data and finding local. But for example, I didn't have time to show it here, but we took the digital doctor system to Kenya, where you would perhaps think, okay, dementia is not at the sort of top list of their kind of worries, but it is actually. They have an increasing group of kind of middle class and upper class people that live longer, as long as we do in the Western world, but they have such a shortage of neurologists. So I think we met most of them up, I don't know, 14 neurologists to the whole of the 60 million people living in Kenya or something, so completely crazy. So they could especially benefit from an automatic tool, for example, on a smartphone, because they're very well connected actually in terms of internet and connectivity.
I imagine that if it's the largest killer, as you mentioned, in Great Britain, is that universal? Like, is that for every country around the world? So there's a kind of like a shared and common interest for the healthcare professionals globally. Yeah,
I would say, and actually a lot of countries have surprisingly good funding for healthcare applications. Not necessarily the UK actually, but, so there's a different kind of levels of kind of interest and funding from in the different countries, I think, and perhaps also. So in the UK and kind of Europe in general, I think we have a lot of companies really interested in this space, which is helping us in academia. So that's for me one of the kind of really exciting things.
Very good. I've just been given the 2-minute nod, so I've got 2 questions left. Okay. Brett has asked, is it possible to generate synthetic data, for example, using GANS scans, to compensate for the lack of data?
Yeah, we have done that, and that's a very good suggestion. So that is possible. It's not always easy. because of course to generate, so this is a technique used a lot in sort of mainstream ASR, but to do for dysarthria, you really have to be able to pick up the peculiarities or characteristics of that person's kind of dysarthria to generate data that actually matches with what they're doing. But that sort of that and voice conversion techniques and those sort of things, yeah, absolutely.
Super. And then finally, the last question goes to Gustavo. Do you think a wearable device or an app would help in closing the gap surrounding data collection needed in this field?
That would be fantastic. It will still, well, it would have certain problems. Ethical is one of them. Recording everything you hear and see is, or at least hear, is problematic. Getting the data labeled is problematic. So mostly we have chosen to ask people to read prompts, because then we know what's been said, but free text is best. So if there's ways around that, that would be great.
Dr. Christensen, super. So that's all we have time for Q&A. I'm going to hand you back to Radine now.
Thank you, Ken, and thank you so much to Dr. Heidi Christensen for a great presentation and discussion, and Ken for facilitating.